Okay. All right, so today first thing we're going to do is finish this problem set, right? It's problem set 5 on chapter 4, a little confusing. And then we're going to get into the next chapter, chapter 5. And the first thing I have to tell you is I made a stupid mistake yesterday. I became concerned about these compliance coefficients here because of Poisson's ratio, right? When you stretch something, it tends to contract. So a positive strain this way causes a negative strain in the opposite direction. And that has to be, in Poisson's ratio, we don't want to deal with that minus sign. So we insert a minus sign in the definition. So in Poisson's ratio, it's a positive quantity. But we know that there's a change in sign when you stretch these positive strain this way, negative strain this way, and vice versa. That has to be in the physics here somewhere. It's in a different, the sign is different here. So there's no problem there. I was just looking for trouble, and I stupidly found it. So there's no problem here. Okay, so we've got one more problem to do. It's number 3. All right. And here's the idea. We have a cube of material, of piezoelectric material, and it's going to be subjected to uniform pressure, also called hydrostatic pressure, equal pressure on all sides. Okay, so the stresses here, remember the stress is the force divided by the area, so it'll simply be the pressure here, although we need to insert a minus sign because of our convention of positive stress causes a positive strain. So we have to technically we have to put a minus sign here. As I've told you, sometimes it doesn't matter, but you should do it just to be careful. So we have the same stress on all surfaces. I've only shown 3 here. There'll be, of course, 6 sides, right? Same pressure on all sides. And here are the general, piezoelectric strain relationships here. And because we're going to operate this as a hydrophone, there will be essentially no free charge. It will be negligible. So the displacement field has to be 0. So that simplifies things a little bit. The tendency here, I think the first time anybody does this problem, and I remember I did it, is to go to the piezoceramic. Remember those? The piezoelectric strain relationships. And here they are written out, and then we did it here. Okay, here are all 6 plus 3. There should be 9 of them, right? 6 plus 3. The tendency is to start with these for this problem we're doing. And then you find out in the next part you can't do that. Because we're going to apply this to lithium sulfate. That's a naturally occurring piezoelectric material, and it doesn't have an axis of symmetry. Like piezoceramics have an axis of symmetry, of rotational symmetry, because they're polarized in one direction. So we have to be more general here. All right? This is too simple, even for us. Unfortunately, even though it's not simple at all, but it's too simple for us. So we have to go to the more general situation. All right. So here they are. I've written these out. I guess I did it. Oh wow. Okay. So I haven't made any. So this isn't. Okay. These have been written out now. They are in general, with one exception. We're assuming that there's no shear stress. All the T4, T5, and T6 have all been set to 0. And T1, T2, and T3 have all been set to minus P. So they could even be more complicated than this, okay? So we've made that specialization. But it's an unbelievable nightmare, right? But again, we specialize. We look at special cases, and we'll get these to collapse down. You'll see. All right, so part B here is if the material were lithium sulfate, what faces would be most appropriate for the application of the electrodes? See, so the idea is this is going to be electroplated on two of the faces. Now, lithium sulfate is this crystal. It looks different in all three directions. It's different. So we're gonna look into which ones we can imagine to be electroded, apply some leads to, and then when a sound wave comes by, we'll be able to pick up a voltage. And if you know the sensitivity, you'll be able to determine the pressure amplitude of the sound wave. So here's, if you look in the textbook, here's the dielectric strain matrix and the permittivity matrix for lithium sulfate. And you can see it doesn't have this axis of, it's got these off-diagonal elements here. For an axis of symmetry, of rotational symmetry, you cannot have off-diagonal elements here for the permittivity, as we discussed. Okay, so now, and I'm just going to illustrate this for you. You should sit down. This is a really good exercise, really good to do once. Take this form and substitute it into here. All right? So, this is one of those things that builds character.
You know what I'm doing Saturday.
Okay, so looking at the D relationships, and that's going to be important. We're going to set D equal to 0 everywhere. But this is going to give us information of what's going on in the electrically, what's going on in the three directions. When you substitute these in, it becomes, this is not bad, okay? That's not bad at all. And now we're about to hit an important point here. Okay? Because it's a hydrophone, all the D's will be 0. There'll be no free charge, or extremely little, negligible. So all the D's have to be 0, no matter what you're picking up, what pole faces you're picking up on. So I want you to focus your attention on the first and the third equations here. We have zeros here, right? Now the best way to look at this is, think of this, there's an epsilon matrix here. It's a submatrix from the original one. It's the 1, 3 submatrix. You can see it doesn't involve, you kill this column and this row, and you get the 1, 3 submatrix. And that's what's involved here. And then we're multiplying it by E1, E3, okay? And it's got to be 0. Okay, do you remember your linear algebra? If I've got a matrix times a vector equaling 0, what goes off in your head? And you want to solve, let's say you want to solve for E1, E3, the vector. You guys know this.
They have to be equal 0?
Why? Yes, but only if what? That certainly is a solution. E1 equals E3 equals 0 is a solution. Is it the unique solution? It's trivial, but how do you know there's not another solution? If the determinant of the matrix vanishes, then you can have other solutions. You don't have independent equations. It's not a unique solution. But here, because these are independent parameters, the determinant's not going to vanish. It would be a weird coincidence if the determinant vanished, okay? So we conclude here that E1 and E3 have to be 0. Okay, so do you want to electrode and attach the leads in the 1 or the 3 the 1 or the 3 direction? Let's see, I didn't label it here, but I guess this is the 1 direction. This is always the 3, and that's the 2. So do you want to put electrodes in the 1 or the 3 direction? It would be pointless. There's no electric field. You won't pick up a voltage. So we have no choice here. This is a good problem, I think. I think I put it in italics, right. The only operation is for lithium sulfate is you got to you got to put the electrodes parallel to the Y, the y-axis, perpendicular to the y-axis, okay, the 2 direction. Now our theory says you shouldn't pick up anything. If you electrode it differently, you shouldn't pick up anything. However, we're assuming uniform fields. This is all, it's buried in here, this is all, we're assuming uniform fields. And that occurs when you have a capacitor where it's close together, right? We've talked about this before. If you've got capacitor plates that are relatively close compared to the area, you're going to have approximately uniform field here. But we have a cube. So do you expect the field to be uniform for a cube? You got a parallel plate capacitor where the sides here are parts of a cube. No way, right? So that bothered me for a couple of years. And you know, these transducer people, they don't tell you the really important things because it's too obvious for them or something. But I finally figured it out, all right? And that's going to be the first page of the lecture we're going to do after we do this problem. I'll explain to you what saves us there. But at this point you would expect, because the field's not going to be uniform, you'd say, oh, you could probably electro and pick up a signal, okay? But you probably can pick up a signal, but it's going to be extremely weak. And I'll explain to you why when we, shortly, okay, after we finish this problem. So we look at the D2 equation. We electroplate in the y direction, we imagine that. And now the sensitivity is the volts, the potential difference divided by the pressure. Volts per Pascal. As we've seen many times, assuming the uniform field, the voltage, the potential difference is just the electric field times the distance. All right. Now, we know what the electric field is in terms of the pressure. Oops, wrong way. Don't we? Mm-hmm. We know from here, maybe I wrote it. We can solve for the electric field here. We substitute that in. We have a pressure in the numerator and the denominator. This is a linear system. The electric field is proportional to the pressure, and the pressure is proportional to the pressure, okay? So they cancel. You can see the linearity there, and we've got now a formula in terms of our material and constants and the dimension here. We've got and that's the whole theoretical point here, in transducers, is to come up to be able to theoretically derive this. Now you can plug numbers in and see if it's reasonable to use as a hydrophone. That's what we'll do next, it looks like. Okay, and again, this is an O here, not a 0. It stands for open circuit. There's essentially no current, which is the normal operation, but not always. But it's the overwhelming. It's almost always open circuit operation. So we can plug numbers in. You look at table 4.4. Brian has all these tables, tons of tables in the book, right? So you look this up and plug the numbers in. And as I told my thesis students, you want to do this on your thesis. It's actually nice to show this. You don't do it in a journal article because people will laugh at you, but they shouldn't. It's really useful to see these numbers here. And in fact, it's especially useful here. What do you see there in those numbers? What do you see here? If you just punch this in, if you go from here to here, you don't see this. You're missing something very interesting here.
D2 is significantly larger than the other two?
Yeah, kind of, but there's competition here. This is hurting us. Okay? It's not a real big deal, but for something besides the lithium sulfate, these could approximately cancel each other, and you'd be in real trouble. Okay? So anyway, and we'll get back to that in a minute. So we get a sensitivity, millivolts per Pascal, sort of typical for hydrophones, typically measured, I think, in millivolts per Pascal. Okay, so D is now, what if the material were PZT5A? Okay, that turns out to be type 2, a type 2, a Navy type 2 piezoceramic, okay, and its properties are tabulated. So now we're going to, instead of lithium sulfate, we now have this. Okay, so this is for lithium sulfate. I mean, that was assumed, right? So we got to go back now. And here are, for a general piezoceramic, it's simpler, no off-diagonal here. We have this axis of rotational symmetry. There's more zeros here, simpler. And now we can look at what we did for problem 1. And this problem set we keep going back to, that's what I guess made me feel it wasn't that bad to actually write all these out here because we keep using it in this problem set. So now it's appropriate to, now we can use this because we have a piezoceramic. Okay, so getting back to wherever we are. Okay, here. No. Yes, for D. Okay. Okay, so they lead to those equations that I just showed you. And now, if you look at the D1 equation and the D2 equations, and the D's are going to be 0, you find that the electric fields have to be 0. So the only way you can make this work is to electrode in the in the direction of polarization. This seems to be a general rule. This bothered me when I first got into this stuff, but it seems to be no point in electroding a direction that's not the direction of polarization of the material. You want to electrode, if you're polarized this way, you want to put the electrodes there. So in here it's very dramatic, you'd get nothing. All right, so we look at the D3 equation, we set D3 equal to 0. We get this, so here we have, we're going down the same road as before, but it's different. We have the electric field is proportional to the pressure. And now we can find the sensitivity. It's the voltage, the electric field, same as before, but it's going to be a different formula because it's a different, has different structures, PZT, than the lithium sulfate crystal. And now we plug the numbers in, and now look what happens. What do you see here? These are tending to pretty well, they don't exactly cancel, but it's kind of small. And so what's the effect? Microvolts per Pascal. We were at milli, now we're at micro. So there's roughly 2 orders, if you compare this to C, it's roughly 2 orders of magnitude less sensitivity. Now you might say, so what? Just get a Stanford preamp. You guys have used now the Stanford Research Systems preamps, right? Those heavy things. They're great. They're worth the $2,500, right? If it's not your money. So why don't you just use a Stanford preamp and just, you got a weak signal, tend to have a much weaker signal. Why don't you, what's the problem with that? What's the potential problem? We haven't talked about this much in this course. Exactly, noise. So this is much lower sensitivity than the other thing. There's an indication you're going to be subject to noise, and the preamp's not going to help you. You're going to amplify the signal. You're going to amplify the noise the same. Okay. So the reason this is so much smaller, part of the reason is clearly this tendency to cancel here. And it's more than that. It's the other parameters too, okay? But that's part of it. Okay, so part E is now. So how can we, if we wanted to deal with this piezoceramic here, how could we boost the sensitivity? Well, if we could somehow shield it from the sound wave such that the pressure only acts on the electroded surfaces, then this would be 0. This is coming about because there's a pressure, it's isotropic, there's pressure, it's hydrostatic, there's pressure on all sides. If we could somehow kill that stress, okay, we'd be killing this right here, this stress right here, and that would help us a lot, as you can see. So that's the subject of part E here, is to imagine that you could somehow shield those other areas so that it's only exposed in the 2 surfaces parallel to the Z direction. And then you kill this, okay, and you just do this is just that with that removed. And now you can see we've gained roughly an order of magnitude by doing that. Okay, let me see if there's, right, okay. So any questions? Yeah.
On the part C, I guess, or whatever.
Yeah, there's too many parts here.
Where you made the argument about the major determinant not vanishing, and so we know the electric field has to be 0 on those.
Oh, that was
those
Here.
those equations.
Yeah, B, okay.
Could you similarly just make an argument that D1 and D3 don't have any relationship with pressure, so there'd almost be no point in using those as well, or is that?
Well, I'd be careful here because you want to, this is not the most general, lithium sulfate's complicated, but it can be even more complicated. And you can get all kinds of coupling in one direction into another direction, mechanically to electrically. So my reaction to what you're saying is I'd be really careful about us making an assumption like that. It may be, here's another way of putting it, and I don't know the answer to this question. It may be in a more complicated crystal that you might be able to pick up something. I would almost bet money on that. That in a more complicated crystal with more coupling, transverse kind of coupling, you probably could operate it. You probably could electrode it in other directions. I feel pretty confident about that, but I don't know. Does that answer? I don't know if that answers your question.
I guess my general question is, we're trying to get pressure signal to produce a voltage in order to use that. And in the 1 and 3 direction, it doesn't seem like that's possible based on these.
Not here, and not for uniform fields.
Okay.
Right, here it's impossible.
Okay, so that would have been my, solving this without the problem set, I would have thought, okay, there's no relationship between pressure and, in the 1 and 3 directions, so I would electrode the 2 directions.
Oh, I see what you're showing mathematically because there's no P down here.
Right.
Okay, again, this can couple, these equations can be more complicated, and you can get, so what you're doing in this case, I guess that's a way of looking at it. It's not real rigorous, but it's just reasonable. In this case, it's reasonable because there's no pressure here.
Okay.
But again, in a more complicated situation, you could get coupling into here. There could be effectively a P down here. But I think that's
for this specific situation.
Yeah, it's not. I wouldn't say it's completely rigorous, but it's good. I think it's a nice, good physical way of looking at it. There's no P down there. Yeah, right. Yeah, that's good. Okay, any other questions or comments? What do I have to do here? Okay, so now we're going to look, and we're going to do something. We're going to start to do something. Well, actually, we might be able to finish a certain topic here, and it's really important. And I distinctly remember when I first went through this stuff that this seemed long overdue. It's actually not long overdue because this is a complicated subject. As I keep telling you, and I think you believe it by now. We're going to actually derive. We assumed a simple electrical circuit, equivalent circuit, for a piezo ceramic vibrator. Very simple, right? It's basically a capacitor that can vibrate. But we're going to actually derive, for a specific case, for a specific geometry, we're going to derive it now. And we haven't done that before, and I don't know if we're going to do it again. It takes some effort, but you can learn a lot from it. So let's do that. Before we do this, I need to, there's a little bit of introduction here that Brian has. Oh, and we're going to address the issue of the uniform electric field. Okay. So we're going to go through a number of examples in this chapter, different geometries of vibrators. So these are vibrator, another word for a projector, something that's emitting sound. Okay. We're going to make extensive use of equivalent circuits, and of course everything's going to be linear. We'll assume that. We're going to neglect internal losses, although Brian slips it in. It's easy when you're dealing with mechanical impedance, and you've assumed negligible resistance. You can always just get it in there. You can just add it to the impedance. Okay, so he actually does this. So this is not completely right here about neglecting internal losses. We're going to do simple cases, simple boundary conditions. And as you'll see, sometimes there'll be unimportant stresses and negligible stresses and strains. They just aren't relevant. We'll neglect them. But I just want to remind you that when the bottom line in this subject is, a real transducer, right? There is a bottom line here, which is not always just. Not all courses are like that. Okay, so you want to be warned that the theory here is just approximate, and it's just expected to get you in the ballpark. Ultimately, as I've told you before, you want to either shove it all on a computer, and I'm sure people do a lot of that these days. It's a lot easier. Once you know COMSOL or some, very elaborate computer simulation package, it's a lot easier shoving this on a computer than building it, okay? But you got to learn COMSOL. How many people use COMSOL? Yeah, you're starting to?
Yeah.
Yeah, good luck. God, it's a pain.
It can do a lot of stuff.
Yeah, it can do it's everything. They say they can do any physics. Any physics they can do. So, and that's, yeah, so it's really useful stuff, but it is really, you'll see. Yeah. And Karuna Suri is an expert, so yeah. So it's good that you're working for him. Okay. Okay. So all right. Now, equivalent circuits are really useful. We've already seen this. You don't want to approach, it's much easier solving something using Kirchhoff's laws than Newton's laws. We've seen that. So that's why from the mechanical side, we come up with a fully, equivalent electrical circuit. So we don't have to worry about Newton's laws. And again, as I was saying, if you want to get more accurate here, you can either build it or you can simulate it and then build it. That's usually the path that people take these days. Now, here's this thing that took me like 2 or 3 years to figure out and still upsets me, okay? I'm trying to remember. It's not in Brian. Brian doesn't make a statement. I'm trying to remember if I looked in other books. I can't remember if I did. No, I don't think I did. Well, I think I might have glanced, but I didn't find it. I think that's what happened, but I'm not sure. Okay, so here's the idea. We have this is a piezoceramic, and it's polarized this way. Okay, these plus, I'm going to have to edit this. These plus signs should be on the other side. This is bound charge. This is the plus and minus due to the alignment of the dipoles, right? As we've seen before, you get this polarization. So here we're going to have net. The charge will cancel here, the bound charge. Here we're going to have a net positive charge. Oh, I have it, sorry, it's flipped here. I have negative here, so it's got to flip this. All right? So this is like a square. We're going to get away from this parallel plate geometry where the plates are close, where we know we're going to have a uniform field. So let's look for trouble here. Think of this like the cube we were just looking at, okay? So without the dielectric here, what do the electric field lines look like? Well, you probably can't solve for them analytically. So if I have two plates here, where the distance of separation is comparable to the to a length of the, to the square root of the area here, something like this. The electric field lines here are not uniform. They'll tend to go something like this. Whoa, they should be kind of more symmetric here. They'll flare out like this, okay? And they'll get a little better here. Okay, then we'll have probably a symmetric line of symmetry there, and then it's reflected here, okay? So they flare out like that. And incidentally, because of that, this charge won't be, if this is a, well, for us, this is, I shouldn't have gotten into this. Don't worry about whether or not the charge is uniform here. But I will tell you, if these are conducting plates, do you think the charge is going to be uniformly distributed there? No, it's not. Okay, it's going to find, it's going to be able to, let's see, I actually don't know the answer to this question. I don't know, it feels like it should be more, it should be denser out here. The charge is is repelling itself. So I think there won't be a uniform charge density. I think it's probably going to be denser out there. It doesn't matter for us because we're going to assume we have a uniform polarization here. Okay, now what happens when you put the dielectric in there? What happens if we were dealing with a magnetic field and we had a highly permeable substance like iron and we put it in there? What happens to the field lines? Do you guys, this is a real practical thing. Transformers. Do you guys know what happens? The lines get essentially trapped. Once you put, it's the same way magnetism and electricity. Once you put this, I don't know if I should be doing this, if you put this material in here with a very high epsilon, permittivity, and you get all this polarization, what happens is the field lines will be trapped in here and approximately uniform. And what's happening there is this. Here's a field line in the absence of the dielectric, right? Once you put the dielectric in there, you can see that because this like if you start off at time t is equal to 0 and you just imagine the dielectric there and you have this electric field, the electric field is going to cause a polarization, right? And this will be like this, and because the electric field's in this way, this will be plus. Once you get this polarization, that has its own electric field. So what is the total electric field going to tend to look like? You see what's going to happen? It's going to push this back in there. That's trapping. And it works for highly permeable material, magnetically permeable, and highly dielectric material. And that's our typical case here. Overwhelming typical case. If you look at tables in the book, you'll see, well, yeah, it's typically quite large. I can't remember it. I can't remember, but this is usually well satisfied. So this is why I think we can get away with this assumption of a uniform field, even though, like in a cube, on a cube, the electric field's not going to be uniform here. But once you put a highly a material with high permittivity in here, these lines will be trapped and will be approximately uniform. So it's not a bad assumption for us, the uniform field assumption, which is very convenient. Okay, so now we're going to begin the problem here. And the problem we're going to solve is a ring vibrator. And so it's, I should have brought, there was one in the lab a couple weeks ago, right? At least one. So this is what it looks like. It's polarized in this direction and electroplated in the same direction on the bottom too. It's got some mean radius, some thickness, and some width. And we're going to assume that it's a thin ring. By that we mean W and T are small compared to A. And I want to make a point of this, and we'll talk about it more tomorrow. We're going to assume, so what happens when you apply a voltage here? Well, the ring's going to strain, right? And as we'll see, the primary mode here is going to be that it's going to go like this. It's going to go like that. And so it can send out sound. It can send out sound here. Now, we're going to assume that there are no standing waves around here. That we're at a low enough frequency so that the thing is uniformly expanding and contracting. All right? And that's going to be important for what we get into tomorrow. And I'll remind you about that. And you'll see it in the theory here. Okay, so we need directions here. We'll call the circumferential direction, we'll call that the one direction. So locally we have rectangular coordinates here. We've seen this before, okay? We're going to call this the x direction, the circumferential direction. We've got to call the polarized, the z direction is in the polarized direction, okay? That's standard. So that's the 3 direction. Okay, now, when this thing strains, because these dimensions are small, because W and T are small, there's not going to be much displacement there, right? The strain is going to be proportional to the overall, the ambient values. You see, we have ambient, this A is an ambient value when you're not driving it, and this W and this T, okay? When you're driving it, you're going to have this value will change. These other values will change too, but because they're small compared to this, they're going to be negligible. So in other words, we can think of this, the same thing happens in a bar, a long bar, a thin bar, okay? The main motion here is going to be, the displacements of the ends here are much greater than the displacements this way. So we don't worry about those. These the displacements that are transverse to our main motion here. All right. So we're going to solve this from scratch. We have to describe the motion. The natural coordinate here to describe the motion is the instantaneous radius. We're going to call, that's going to be what we call A, the ambient value, plus zeta. So zeta is the displacement from, the radial displacement from equilibrium. Okay, we're going to call that zeta. And we need to get an equation for zeta. We have to solve this. The particle velocity is, of course, just the time derivative of zeta. Zeta is instantaneous, it's a function of time. And to connect all this up, because we have stress-strain relations, we have strain and displacement field relations here. To connect this up, we look at the strain. If you look at this little bit of material here, and look at the strain in this direction, in the radial direction. Okay, what is it? So you can look at this. We should go to the mean value here. We should go to the ambient value. So you look at, this is equilibrium, right? There's an arc length there that's equal to A times delta theta. When this thing is expanded, in the one direction, there's a displacement, right? It's strained. The instantaneous displacement there, that arc, has instantaneous length. The total radius, the ambient plus the change, times the angle, right? To get the strain, we take the instantaneous displacement, we subtract off. This is the instantaneous length, okay, of the arc. So if you look at an arc at the midpoint here, as it goes out, it's straining, right? It's going like this. So here's equilibrium. When the thing's out here, this is strain. When it's down here, it's compressed. Okay, so the strain is going to be this length minus the equilibrium length divided by the equilibrium length. So that's exactly what we've got here. It's the change in length, that's what this is, divided by it's a dimensionless quantity. That's the strain, as we've defined it. Okay, and look at this. You can do this in your head. It's a nice, simple relationship in terms of zeta. Okay, so here we go. We're going to go now for Newton's second law apply mechanics here and find out equation of motion for this zeta coordinate. You'll notice here that these two forces don't exactly cancel because of the curvature here. There's going to be a net force. And this ought to look very familiar to you. Remember 3119? I know it was a long time ago. This is very similar to waves on a string under tension. When you have waves on a string under tension, you have the string here, and you look at a little element here. There's a tension force here, there's a tension force here for linear motion. Those two magnitudes are approximately the same, but their directions are a little different, right? There's a net force wanting to bring this back, a net restoring force. So we can use the mathematics from there. You can show that the net force, and you did this for a string, the net radial force is going to be inward. It's going to be restoring it So for a positive displacement, the force is this way. For a negative displacement, the force is that way. So we have a minus sign. It's proportional to the tension. In our case, we're calling that F1. Okay, and it's proportional to this distance here, the force. As you shrink this down, the force is going to go to zero because these will become anti-parallel. Okay, so this is what you would expect, and this is what you did in 3119. So there's the force. There's the net radial force. Okay, the force in terms of the stress is just going to be T1 times the area. The stress is the force per unit area. So we have that. Okay, the mass of our element here, well, that's easy. It's just the mass per unit volume times the volume of the element. All right, so F equals ma, or ma equals F. The mass times the acceleration, two time derivatives on zeta, is the force. And now what we can do is, you might say, oh, let's cancel the delta thetas. Well, you actually don't want to do this here. We want to integrate over the whole ring. We're just dealing with an element of the ring. It's a trivial integral to do because we have isotropy. We're assuming, no radial, no azimuthal motion. The ring can actually go like this. That's outside of our theory, okay? And again, we'll talk more about that tomorrow. So we just integrate this over theta, and this comes outside the integral. This is just going to be the total mass of the ring, where I'm summing up all the mass here. And on the opposite side, we're going to get a 2 pi times the circumference, so essentially. So we get this. So that's what we get from Newton's second law. And the mass of the ring is given by this, just the density times the volume. And now we can look at the piezoelectric strain relationships. What's relevant for us is the strain relationship in the one direction. And we'll get to this later, the displacement in this polarized direction, displacement field in the polarized direction. And incidentally, is this going to be zero?
Yes.
What are we doing with this thing? It's a vibrator, it's a projector, it's a transmitter. You got to supply current to it. It's not going to be zero. So trouble's on its way, okay? we can't set that equal to zero, but we'll get to that. Okay, so we look at the first equation. We can solve it for the stress, okay, this T1 here. We've got to get a differential equation just in zeta, and this is changing with zeta. We got to just beat it down to one variable. So how do we do that? We look at this relationship here, solve for the stress. We know what the strain is in terms of zeta. We just talked about that, right? That's nice and simple. It's just zeta over A. So that's good. And now we've got it, okay, this is good. We've got zeta. We have this this is like a drive. That's what's driving this motion. So we'll keep that, okay? We can now take this and substitute it into there, and this is the equation that we get. Now, some symbols are being used here. You'll notice in Newton's second law, the coefficient of this would be the stiffness, K, usually called K, Hooke's law constant, right? 1 over that is the compliance. So instead of carrying around all these quantities, we're just going to call it what it is. It's the mechanical compliance. So we'll use that there. All right. And now, you've all seen this before. If this is zero, what do you have? What kind of motion is this called? Simple harmonic motion, right? And this E3 is going to be oscillating. So this is driven. This is a directed drive on a simple harmonic oscillator. Simple. And the solution, very easy. There's going to be a homogeneous solution. We don't care about that because with a little bit of damping, that's going to die away. What we care about is the steady state solution, right? Due to this oscillatory drive. So we'll take it to be oscillatory here. That's what I'm doing there. And now I'll let you confirm this if you're interested. It's easy to get the solution here. It's this. It's easy to solve this differential equation, what we call the particular solution. You know it's got to go like e to the I omega t, and then you just solve for it. It's very easy. You did a lot of this when you dealt with a harmonic oscillator in 3119, this kind of thing. Okay, now, something else has happened here. Where did that come from? Well, there's a lot of, the constants are getting mixed up here. Here's the, we can identify the mechanical impedance in there. It's very convenient. And then if you want to add damping, you just add a real part to this, right? It's easy if you want to put that in there. Okay, now that's the easy part. Well, yeah, so that's the easy part. Now we got to confront the electrical part, and where D3 is not equal to 0, because we've got current flowing, and there will be free charge. So this is the first time we've done this, okay? So let me tell you how this works. Look at my notes here. Right. So there will be there's some bound charge. There's going to be, in the material here, there'll be some bound charge. We don't have any control over that, but we do have control over the free charge, and the displacement field is dictated by the free charge. And the way it's, I should have added this. I don't know earlier in the course if I wrote this down. This is one of Maxwell's equations for a medium, you know, where we're dealing with the displacement field. Does you guys recognize this? Okay, so we can apply this to our simple uniform field case here. We use, we convert this into an integral. We integrate this over a volume. And when you integrate this over a volume and you have a uniform D field here, what you find is that you integrate over a little pill box. That's the standard approach here. On the right-hand side of the equation, when you integrate over that pill box, you're just going to get the charge. That's going to give you the free charge, okay? And when you integrate this, this is just going to be D3 times the area of the pill box. So we end up with this real simple relationship right here. And now, why is this important? Well, what's the current? It's I omega q. It's dq dt, which is I omega q. So, and the current is one of our good variable that we need to deal with. Yeah, okay. So, okay, so what we can do here now, at this point, is so we can find D3 from here. Okay, and now we know T1. You want to imagine substituting this expression into here. So now we've got everything in terms of our drive. We've got D3. Now we can get the charge. And when you do that, this is what you get. Okay. So this is the charge, the instantaneous charge in terms of zeta. This is the contribution due directly to the electric field. This is due to the contribution, the coupling, due to the fact we have mechanical motion here, which influences the charge. This right here. Now, I don't know if you remember, but this might look familiar to you. That's the coupling coefficient, the square of the coupling coefficient. So we'll just start, instead of dragging this all around, we'll just call it that. All right, so I'm going to finish this right now. We won't get quite, it's okay. We won't be able to quite finish this derivation. It's good to look at the admittance here. It's better to look at the admittance. It's simpler, as we've seen before. The input admittance is the reciprocal of the impedance, so it's the current divided by the voltage. Okay? The current, as we said before, is just I omega q. Okay? Now I haven't put down all the steps here because it would be too long, but we know what zeta is. Remember, we know zeta in terms of E3. We have the solution here. So I want you to imagine that you take this and substitute it into here. Now this is all, and we get the current. It's all proportional to E3. Okay? The voltage is also proportional to E3, of course. We've seen that many times. So E3 will cancel, in the admittance, and this is what we get. Now these things have switched. This one's for the standard form. We put this one down here, and the electrical one down here, and the mechanical one down here. So we see that the total input admittance is the sum of two admittances. There's an electrical and a motional or mechanical admittance, and the meaning of the electrical is it's when there's no motion, no mechanical motion, blocked. Okay, and we can identify here it is. It's right here. Okay, and you can see it's I omega times some constants. What do we call all this? What's the admittance of a capacitor? I omega C. So this is the blocked electrical admittance. All of this right here, which we call C0. On the mechanical side, okay, when we look at the motional admittance here, it's 1 over the impedance. And then there's this quantity right here, which has dimensions. And it's natural to call that n squared, as you'll see. Right? So we're almost there. We're going to have to stop, but we're almost there. Brian jumps to this circuit. He really shouldn't have done that, but we'll explain it. We're essentially there. We've essentially derived. Once we remove this transformer, we're going to get a circuit that you guys are well familiar with for described piezos. We've done this before in class and in the lab. So we've actually derived in this case, and we derived all the constants too. But we'll pick this up tomorrow.